In this section, we're going to look at electric field. Electric field. Now, if you remember, Coulomb's law says that you've got two charges, like over here. This charge will somehow exert force on this charge, even though there is nothing in between. Okay, so that bothers some people. It doesn't make sense. You got this charge, there's nothing between them, and yet these two charges are able to exert forces on each other. Okay, so a theory that we call field theory tries to explain this situation. So let's state what the field theory is. Field theory. Field theory states that the mere presence of this charge brings about change throughout space. The mere presence of this charge over here will bring about some change throughout space. And when a charge is placed at any point in that space, that change brought about by this charge will produce force on this charge. Okay, so this theory states that the mere presence of a charge brings about some changes throughout space, and when a charge is placed at any point in space, that change brought about by this charge will exert force on that charge. Okay, so field theory says that the presence of a charge brings about change throughout space, brings about changes throughout space. That change exerts force on a charge placed at any point, Okay, so instead of saying that this charge somehow exerts force on this one miraculously, this theory says the presence of a charge brings about changes throughout space, and when you place certain charge at certain location, it's that change brought about by this charge that produces force on this charge. So there is a field produced by this charge throughout space. That's what we call the field. Okay, there is a field produced by this charge, and it's that field that exerts force on a charge placed at any point in space. So the field is just a property of space. It exists anywhere, whether there's a charge in there or not. So the field is a property of space. You don't have to have a charge point to have this field. This field is there. It's a property of space. So this electric field should be defined in such a way that depends on space and not on a charge placed at a certain location. So how do we do that? The way to do that is we can define it to be as the force exerted per a unit charge. If you define the electric field to be the force exerted by a unit charge, then it doesn't matter how much charge you put in there. It's always the same. It becomes a proper space. At a certain location, it would be the force exerted on a unit charge. So it doesn't depend on the amount of charge placed at that location. So that's how we define electric field. Okay, let's say you got this charge Q over here, and you got this point over here, point P. The electric field at this point is defined to be the force per unit charge. You place a certain charge in there, you measure the force, and then the force per unit charge is what you call the electric field. So it's the force that will act on a unit charge that we call electric field. So it doesn't depend on the amount you put charge in there. Okay, so let's define electric field. Electric field is defined to be as the force per a unit charge placed at the given point. Okay, at the given point. So mathematically you can say electric field E equals the force that will act on the charge Q placed at the point divided by the charge. Okay, so the electric field is force per a unit charge. If you want to find the electrical dislocation due to this charge, what it is, you place a test charge in there, you measure the force, you divide the force by the charge, that'll give you the electric field at the given point. But this is customarily written as F equals charge times E. Okay, the force equals the electric field at the point times the electric field. So the magnitude equation would be simply the magnitude of the force equals absolute value of the charge times the magnitude of the electric field. So this is a vector equation, this is a magnitude equation. How about for direction? You see, if charge is positive, the electric field has the same direction as the force acting on the charge. But if the charge is negative, you see these two will be opposite of each other, so the electric field will have opposite charge to the force acting on the charge. Okay, so let's look at the direction. If Q is positive, then the electric field is parallel to the force. The force and the electric field will have the same direction. But obviously, if Q is negative, then the electric field is opposite or anti-parallel to the force. Okay, so in this case they're parallel, the electric and the force, but in this case they are opposite. Okay, so if you want to find the direction magnitude of a certain electric field at a given point, the best thing to do is put a positive test charge at that location. Okay, so if this charge is positive, then the electric field and the force will have the same direction, right? So if this charge is positive, we know the force will be this way because they're going to repel each other. So that tells you the direction of the force will be this way. If the charge is negative, if this test charge is positive, then the direction will be this way. Okay, so that tells you when this charge is negative, the direction of the electric field will be this way, the same as the direction of the force acting on the positive test charge. All right. So let's look at an example. Let's say the electric field at point P, let's say is maybe 4 Newton per Coulomb North. Okay, let's say find the magnitude and direction on a 2 Coulomb charge placed at the point. Okay, so what we have is, we know the electric at certain point, it is 4 newtons north. This is the electric field. So the electric field equals 4 newtons north. Now this question is asking, what will be the force exerted on a 2 Coulomb charge placed over here? Q equals 2 Coulomb placed over here. Okay, so the force is, this we're looking for, force equals Q times electric field. Okay, first let's do the magnitude. Force equals absolute value of charge times electric field. The magnitude of the electric field is 4 newtons. Okay, the charge, which is positive in this case, but also your charge would be 2 coulombs. So the force would be 4 newtons times 2. No, this is charge times electric field. So this is the electric field is per coulomb, and then we got 2 coulomb over here, so you get 8 newtons. That's the magnitude. Now let's look at the direction of the force. Now remember, if the charge is positive, electric field and force are parallel. Okay, so since the electric field is north, the force will be north. Okay, so direction will be north. Okay, because the charge is positive. If the charge is positive, the electric field and the force have the same direction. B, let's say, find the magnitude and direction of the force when, let's say, a negative 2 coulomb charge is placed at point P. Okay, so the magnitude is going to be absolute value of the charge times the electric field. Even the charge is negative 2, then its absolute value will be 2, and the electric field is 4 coulombs. This is 4 newton per coulomb. We get 8 newtons. How about direction? Now the charge is negative, so the electric field and the force are opposite. So if this is north, the force is going to be south. Okay, so the direction is going to be south. The electric field and the force have opposite directions if the charge is negative. All right. Now let's look at the electric field due to a point charge. Electric field due to a point charge. Okay, so here's a problem. We have a point charge Q over here. Okay, we want to find an expression for the electric field at this point. Let's say it's point P. Okay, so let's say the distance is R and this charge is Q. So to find the electric field over here, what you have to do is we're going to place a test charge Q prime over here. Let's assume it's small so it doesn't disturb the field, and it's greater than 0. Okay, then you measure the force on this charge and then divide by this charge. Okay, so but we know the expression for the force by Q on Q prime from Coulomb's law. Okay, so the electric field at point P is going to be the force on Q prime divided by Q prime. Okay, but the force on Q prime from Coulomb's law, it's K, absolute value of the charge. Now this is positive, so we don't have to put an absolute value. Okay, we're assuming it's positive. All right, so Q prime divided by, let's say this distance is R, divided by R squared. This is a force. Okay, so the electric field at point P is the force on Q prime divided by Q prime. Okay, and that is Q, absolute value of Q times Q prime, R squared divided by Q prime. Okay, so you see this Q prime goes away. Remember, electric field is independent of the amount of charge you place at the point. So we get the following formula for the electric field due to a point charge. It's simply K, absolute value of the charge, divided by the distance squared. So that's how you calculate the electric field due to a point charge. Okay, this is the charge that's producing the field, and R is the distance between the charge and the point at which the electric field is being calculated. Okay, Q is the charge producing the field, and R is the distance between the charge and the point at which the electric field is being calculated. Okay, so that's the magnitude. Now let's look at direction. So there are going to be two different directions for a positive charge and negative charge. Now, if this charge is positive, what's going to happen? Our test charge is positive, okay? And the electric field and the force have the same direction if this test charge is positive, right? Now, if this is positive, then they're going to repel each other, all right? So you see, if this charge is positive, the direction of the electric field at point P is radially outward, away from the charge along the line joining the point and the charge, okay? So if the charge is positive, the direction is radially away from the charge, radially away from the charge, okay? You see, our test charge is positive. If this charge is positive, then the electric field and the force have the same direction. But if both of them are positive, the force is repulsion. The direction of the force is radially away. Therefore, the direction of the electric field is also going to be radially away. Okay? How about if Q is less than 0? Let's see what happens when the charge is negative. Remember, if this charge is positive, if this charge is positive, the direction of the electric field is the same as the direction of the electric force. Now this is negative and this is positive, the direction of the force is attractive, which is also the direction of the electric field. Okay, so you see, if the charge is negative, the direction of the electric field is radially towards the charge, is radially towards the charge, radially towards the charge. Okay, so if you've got a positive charge over here, you're looking for the electric field over here, it's going to be this way. If you've got a negative charge over here and you're looking for the electric field over here, this is point P, it's going to be this way. Okay, so the direction of the electric field is radially outward if the charge is positive, radially inward if the charge is negative. Okay, so you see, if you have a positive charge over here, if you take this point, it will be this way. If you take this point, that's going to be radially outward. If you take this way, it will be like this. If you take this way, it will be like this, and so on. Okay, if you take over here, it will be like this. But if this charge is negative, it will be radially inward. If you take this point, it will be this way. If you take this point, it will be towards the charge. If you take this way, it will be this way, and so on. Okay, that's what we mean by radially outward. So the electric field due to a point charge is proportional to the magnetic charge, inversely proportional to the square of the distance. And if the charge is positive, the direction is radially outward. If the charge is negative, the direction is radially inward or towards the charge. Okay. Now let's consider an example. Suppose we have the following charge over here. Let's say this is maybe 2 microcoulomb, okay? And we want to find the electric field at this point. Let's say this distance over here is maybe 2 millimeters, okay? So the magnitude is the formula K, absolute value of the charge divided by the distance squared. Okay, and charge is positive, so it's just going to be 2 times 10 to the power negative 6. So you've got 9 times 10 to the power of 9 for the constant, 2 times 10 to the power negative 6 for the charge, divided by the distance. The distance is 2 millimeters, or 2 times 10 to the power negative 3 meters, right? Squared. So let's look at the numbers first. One of the two cancels out, so you got another 2, that's 9 over 2, or 4.5. Okay, so you've got 9 over 2. Let's look at the powers. You got negative 6 over here plus 9, that's 3, but you got another 6 from the bottom, so it's going to be 10 to the power of 9 Newton per Coulomb. Okay, how about the direction? The charge is positive, therefore the direction is radially outward this way. Okay, so it's east, and the direction is east. Direction is going to be east because it is radially outward. Okay, how about if it was a negative one? Let's say this is negative 2 microcoulomb, and this is point P, and then we have the same distance, 2 millimeters. Of course, the magnitude will be still the same, okay? Because you've got E, K, absolute value of the charge, divided by distance squared. So absolute value of negative 2 microcoulomb is still 2 microcoulomb. So we'll get the same answer like this one because all the numbers are the same, okay? 10 to the power of 9 Newton per Coulomb. How about the direction? It's negative, so the direction is radially inward or towards the charge, okay? So the direction is going to be west, all right? Direction is going to be west in this case. That is towards the charge or radially towards the charge. How about if you've got the number of charges in the vicinity of a point? How do you calculate the electric field? So we're going to look at superposition principle. Superposition principle. Superposition principle. Okay, so let's say we're trying to calculate the electric field at this point, and we've got a number of charges over here, Q2, Q3, and so on. So how do you calculate the net electric field? All it is, you obtain the electric field is this charge, the electric field is this charge, the electric field is this charge, then you add them vectorially. They're vectors, they should be added like vectors. So if there are a number of charges in the vicinity of a point, the net field is the vector sum of all the fields due to the individual charges, Okay, you simply obtain the electric field with each charge and then just add them. Okay, so the net electric field at point P is simply the sum of the electric field due to charge 1, electric field discharge 2, electric field discharge 3, and so on. The same pattern continues. All right, so that's how we find the electric field due to a number of charges. All right, now let's consider an example. Suppose we have, let's say this charge over here is Q1 is, let's say, negative 2 microcoulomb. We have another charge over here, Q2, let's say it is 4 microcoulomb, and then we have another charge over here, let's say negative 1 microcoulomb. Let's say this is Q3, okay? And let's say these distances are 1 millimeter, and this distance is also 1 millimeter. Okay, so the question is calculate. Oh, this is not a charge, this is a point, I'm sorry. This is a point P, there is no charge over here. Okay, we want to calculate the net electric field at point P. The question is calculate the net electric field at point P. Okay, so there are two charges causing electric field at this point. So we're going to obtain the electric field is charge 1, the electric field is charge 2, and then we're going to add them both. Okay, so the net electric field at point P is the electric field due to charge 1 plus the electric field due to charge 2. Okay, so we're going to obtain these two electric fields. Let's start with E1. Let's start with E1. E1. First we're going to the magnitude. The magnitude is E1 K, absolute value of the charge Q1 divided by the distance between 1 and point P squared. Okay, so let's get the numbers. Q1 is -2 microcoulomb. This is -2 times 10 to the power of -6 coulomb. And then let's look at the distance. This is the distance between 1 and point P. That is 2 millimeters. Okay, from here it is 2 millimeters. So the distance between charge 1 and point P, this R1P, is 2 millimeters, or 2 times 10 to the power of -3 meters. Okay, so now we can calculate the magnitude of the electric field. That's 9 times 10 to the power of 9. And then the charge Q1, remember it's negative, but this is absolute value, so it's going to be 2 times 10 to the power of -6 divided by 2 times 10 to the power of -3 squared. Okay, so from the numbers, we have 18 divided by 4, or 9/2. Okay, so we have 9/2, and then from the powers we have 9 -6, that's 10 to the power 3, but then you got -6 from here, and when it goes up it's going to be positive, so you got 10 to the power of 9 Newton per coulomb. Okay, how about the direction? Now let's look at the direction. Remember, the direction is, if the charge is positive, it's radially outward. If the charge negative, it's radially inward. So this is negative, so the direction is going to be radially inward towards the charge. Okay, this would be the direction of E1, which is west. So direction for this electric field is west. This is the magnitude, and the direction is west. So the x component of this one, it just is going to be negative because it is west. Okay, or the angle is 180 degrees. So the x component is -9/2 times 10 to the power of 9 Newton per coulomb. Okay, so we don't have vertical components in this case, so we're just dealing with x components. All right, now let's look at the other electric field. That's E2. First, let's look at the magnitude. E2 is K, absolute value of the charge Q2 divided by the distance between charge 2 and P squared. Okay, let's look at the charges. Q2, the charge of Q2 is 4 microcoulomb. That is 4 times 10 to the power of -6 coulomb. And then the distance between charge 2 and point P is 1 millimeter. This is distance over here. That's 10 to the power of -3 meters. 10 to the power of -3 meters. So we can calculate it. So you've got E2 equals 9 times 10 to the power of 9. The charge is 4 times 10 to the power of -6. The distance is 10 to the power of -3 squared. Okay, so from the numbers we get 36, and from the powers, 9 minus 6 is 3, then plus 3 is 9, times 10 to the power of 9 Newton per Coulomb. Now let's look at the direction. Remember, if the charge positive, it's radially outward. If the charge negative, it's radially inward. So this is positive. So E2 is going to be radially outward. E2, okay? That is east. So the direction is east, and the component is going to be positive because east, okay? E2x, there is no y component. It will just be 36 times 10 to the power of 9 Newton per Coulomb, okay? Now we can add up the two components. We have only x components, so E net x, which is simply the x component of the net electric field, is E1x plus E2x, okay? So we obtain for E1x negative 9 over 2 times 10 to the power of 9, or negative 4.5 times 10 to the power of 9 Newton per Coulomb, plus the x component of the second electric field, which is 36 times 10 to the power of 9 Newton per Coulomb, okay? So this is 31.5 times 10 to the power of 9 Newton per Coulomb. Now you see the x component is positive, so that means the direction is east. So we can say the net electric field has this magnitude times 10 to the power of 9, and the direction is east because the component, the x component, is positive. All right, so this is a one-dimensional problem where all the electric fields are in the same direction, the same line. Now we're going to look at a two-dimensional example. Okay, suppose we have the following situation. Okay, suppose we want to calculate the electric field at this point. This is our point over here, okay? And then we have, let's say we have a charge of maybe 2 nanocoulomb over here. Let's call it Q1. And then we have a charge over here, Q2. Let's say it is negative 1 nanocoulomb. Let's say this distance over here is 4 millimeters, and this distance over here is 3 millimeters. Okay, so we have two electric fields. The electric field at point B due to charge 1, and the electric field point P due to charge Q2. Okay, so the net electric field at point P at this point is going to be the sum of the electric field due to charge 1 plus the electric field due to charge 2. Okay, so we're going to look at these two electric fields separately, then we're going to add them. E1, okay, let's look at this one. First, let's see the magnitude. The electric field is discharge is K, absolute value of the charge, divided by the distance between 1 and P squared. Okay, so Q1 is 2 times 10 to the power of negative 9, okay, and the distance is the distance between the point and the charge is 4 millimeters, okay, so R1P is 4 times 10 to the power of negative 3, okay, so let's calculate it. So you've got 9 times 10 to the power of 9, and then the charge is 2 times 10 to the power of negative 9, okay, and the distance is 4 millimeters. That's 4 times 10 to the power of negative 3 squared. Okay, so if you look at the numbers, we have 18 over 16 or 9 over 8. Okay, so we have 9 over 8, and if you look at the powers, these two go away. We have negative 6 when it goes up, becomes 6 times 10 to the power of 6 Newton per Coulomb. Okay, now let's look at direction. Now this charge is positive, okay, If the charge is positive, it's going to be radially outward. Okay, if you put a positive discharge over here, it's going to push it away. So the direction of the electric field at this point, this one over here, is south. Okay, it is discharge. Since discharge positive, the direction will be radially outward or radially away from the charge. Okay, so the direction is south. Or if you want to talk about angle, you see theta 1. If you come this way, it's 270 degrees. If you come this way, it's negative 90 degrees. So you can say negative 90 degrees, that's 90 degree clockwise this way. So that's the direction of E1. So we have the magnetic direction. We're going to do the same thing for E2. For E2, first we're going to do the magnitude. The magnitude is K, absolute value of charge Q2 divided by the distance between 2 and P squared. Okay, so let's look at Q2. Q2 is located over here and it's -1 nanocoulomb. Q2 is -1 times 10 to the power of -9 coulomb. How about the distance to P? The distance between Q2 and P is distance over here, and that's 3 millimeters. It's 3 millimeters, or 3 times 10 to the power of -3 meters. Okay, so let's calculate it. This is 9 times 10 to the power of 9. Q2, you see it's absolute value, so we can use positive over here. 10 to the power of -9 divided by the distance squared, 3 times 10 to the power of -3 squared. Okay, so from the numbers we get 9/9, that's 1. Okay, 1. How about from the powers? We got 9 minus 9 is 0, but you got 6 from the bottom, times 10 to the power of 6 coulomb. Okay, how about the direction? This is Newton per coulomb, sorry. How about the direction? The direction, you see, Q2 is negative, so the direction is towards the charge. Okay, the direction electric over here is going to be inward towards the charge. So this is the direction of E2. Since this charge is negative, the direction of the electric field is towards the charge, so it's east. Okay, direction is east, and the angle is going to be theta to east is 0. Okay, so we have the magnitude and direction for both electric fields. Now we're going to use the rules of vector addition to add these two vectors. Now in this case, you see they're perpendicular to each other. You can basically use Pythagorean theorem to do it, but to be technical about it, I'm going to use the formulas for vector additions to do it. Okay, otherwise this is not very difficult. You get the force, the sum is over here, and then after you find the magnitude of this one, you can also calculate the direction using tan inverse. But let's do it using the general rule, just to be technical about it. Okay, so now we're going to the components. We're going to the components, and then we're going to use the sum formula. Okay, so what do you know about E1? We know the magnitude. The magnitude for E1 is 9/8. E1 is 9/8 times 10 to the power of 6 Newton per coulomb, and south, or the angle, is -90 degrees. Okay, so that means E1x is E1 times cosine of theta 1 equals 9/8 times 10 to the power of 6 times cosine of -90. Of course, it's going to be 0 because it's a vertical force. It doesn't have a component. Okay, it's going to be 0. How about E1y? That's E1 times the sine of theta 1, okay? That's 9 over 8 times 10 to the power of 6, and then sine of negative 90 degree. This is negative 1, okay? So we get negative 9 over 8 times 10 to the power of 6 Newton per coulomb, okay? So this is for E1. We're going to do the same thing for E2. For E2, okay? E2x would be E2, which is over here. That's 1 times 10 to the power of 6, and the angle is 0. Cosine of 0, which is 1, we get 1 times 10 to the power of 6 Newton per coulomb. E2y is going to be the magnitude times the sine of 0, which is 0. Okay? Alright, now we're going to use the formulas for magnitude and direction. First, let's do magnitude. Okay, so the magnitude of the net is square root of E1x plus E2x squared plus E1y plus E2y squared, okay? First, let's put in the zeros so that you can see this is actually Pythagorean theorem, okay? So, E1x is 0, okay? This one over here is 0, and also E2y is 0. This one is 0, okay? So this turns out to be square root of E2x squared plus E1y squared, okay? So it basically turns out to be Pythagorean theorem, okay? So plug in the numbers, so you get square root of E2x this is E1, oh, E is over here. So E2x is 1 times 10 to the power of 6. This is 1 times 10 to the power of 6 squared. And E1y is negative 9 over 8 times 10 to the power of 6 squared. So that's the magnitude, okay? So you can factor out 10 to the power of 6 out of this. So you get square root of 1 squared, which is 1, and then 9 over 8 squared, okay? We can calculate this one. Well, let's do it over there. Okay, the direction, that's Newton per coulomb. And the direction for the net angle is tan inverse of, you add the y's, you divide by the sum of the x's. 2x, okay? So we just saw that E1x is 0, this goes away, and E2y is also 0, goes away. So this is tan inverse of E1y divided by E2x. Okay, so you can plug the numbers. That is tan inverse E1y is this one over here. Okay, that is negative 9 over 8 times 10 to the power of 6, and then E1x is 1 times 10 to the power of 6. Now remember, it's y that's negative, not the x. It's only when the x is negative that you add 180 degrees. Okay, so in this case we don't add 180 degrees, so it's basically tan inverse of negative 9 over 8. Okay, so we have the magnitude and direction. Finally, we're going to look at electric field lines. Electric field lines. These are lines used to represent electric field. Remember, electric field is a proper space. It has a value at every point in space, okay? So these are lines that represent electric field geometrically. So you can say these are lines that represent electric field in space. Electric field in space. This is a property of space. All right. So if these lines are to represent electric field is a vector. It has two properties. It has direction and magnitude. So these lines should be able to represent both the magnitude and the direction. So let's see how these lines represent the magnitude and the direction of the electric field lines. First, let's look at the magnitude. The magnitude is represented by the density of the lines, or by the number of lines that cross a unit perpendicular area. This is represented by the number of lines that cross a unit perpendicular area. Okay, the greater the number of lines per unit perpendicular area, the greater the electric field. In other words, the denser the lines, the greater the electric field. Or you can say, or by the density of the lines. By the density of the lines. Let's say you have this kind of electric field. It gets less dense and less dense as it goes away. So that means the electric field over here is bigger than the electric field over here, because the electric fields are denser over here, or the number of lines per unit perpendicular area is bigger over here than over here. Okay, so the electric field over here will be bigger the electric field over here, because the magnitude of the electric field is represented by the density of the lines, or the number of lines that cross a unit perpendicular area. Okay, so these lines are drawn in such a way that the density is proportional to the electric field. How about direction? Okay, direction. Okay, the lines are drawn in such a way that the line tangent to the curves at any point gives you the line of action of the electric field. Okay, so the line tangent to a curve at a given point gives the line of action of the electric field at the given point. Okay, for example, let's say this is a line, okay, and you're looking for the electric field at this point. So if you draw the line tangent this curve, remember tangent means line that touch the curve at one point, you get this line. So that gives you the line of action of the electric field at this point. But there are two possibilities. It could be either this way or this way. Okay? So how do you distinguish between these two directions? To distinguish between these two possible directions, an arrow is placed on the line. So if I put this arrow, it means I pick this one over here, but if the arrow is the reverse, I pick this one over here. Okay? To distinguish between the two possible directions of the line of action, an arrow is placed in the curves. So to distinguish between the two possible directions, an arrow is placed on the curves. An arrow is placed on the curves. Okay? So that way you can determine the electric field uniquely. Okay? The tangent line gives you the line of action of the electric field, where there are two possible directions. Okay? And an arrow placed on the curves determines which electric field the right one. If the arrow this way, you pick this direction. If the arrow this way, you pick this direction. Okay? So that's how electric field lines represent electric field. Their density represents the magnitude, and the tangent line and an arrow give you the direction of the electric field at any point. Alright, now we're going to look at electric field lines due to point charges. Electric field lines due to point charges. Okay, let's start first with a positive point charge. Positive point charge. Okay, suppose we have this positive point charge. All right, now if you remember, the direction of the electric field due to point charge is radially outward. So if you take this point, it will be this way. If you take this point, it will be this way. If you take this way, and so on. So you see, this will give you the electric field lines. You can do this in any direction. You can do this way, take this way, it will be this way, and so on. So you'll have this one, you'll have this one, you'll have this one a similar way. Okay, so that's what the electric field lines due to point charge looks like. Okay, it's radially outward. As you can see, the density decreases as you go farther and farther. You see the density of the lines. As you go farther and farther, the density of the lines decreases. The number of lines remain the same, but the area is increasing as you go up. So the result, the magnitude of the electric field will decrease inversely proportional to the square of the distance, because the area decreases inversely proportional to the square of the distance. All right, now we got the lines. You got to put arrows. The direction is this way, right? So we have to put arrows like over here to tell the direction is radially outward. Okay, B, negative charge. Point negative charge. It's going to be the same thing, except that the direction is going to be towards the charge. Okay, take this point, it's going to be this way, take this one this way, and so on. Okay, so this line, but the arrow would go this way. So this, you can do this in any direction. The arrow goes this way, the arrow goes this way, the arrow goes this way, and so on. This way, and so. So this will be the electric field due to a negative point charge. All right. Now let's look at a negative and a positive. A positive and a negative point charges. Point charges. Okay, so let's say we have a positive over here and negative over here. Now remember, the net electric field is the sum of the electric field is these point charges. Okay, let's say these two charges have the same value. Okay, so if I take this point, you see the electric field, this one would be, this closer is going to be bigger, this farther is going to be smaller, so the net is going to be this way over here. Okay, this is going to be pushed, or no, I'll say that differently. If you take this point over here, this is pushing, this is attracting, so the indicator will be this way. Okay, so the electric field will go this way, will go this way. You see, this one is pushing, this is outward, this is inward, they're both in the same direction, they'll just add up. Okay, so this way. Take a point over here. This charge will be radially outward like this, but this charge will be radially inward like this. Okay, but this will be smaller than this one because this is closer. Okay, so it'll be something like this. If you do that to all the points, you will get something like this. This is what the electric field lines look like. Like this. And the direction is from the positive toward the negative. You see? It's very easy because this is pushing this way, it's attracting. This is radial outwards, radial inwards, there in the same direction. Okay? So what do we see from here? Electric field lines originate from a positive charge and they sink in a negative charge, generally true. So let me say that electric field lines originate in a positive charge and sink in a negative charge. This is true about any electric field line. It has to start from a positive charge somewhere and end a negative charge somewhere. Okay? Now, let's take two positive charges. Two positive point charges. So let's say we have this positive over here, this positive over here. Now look at the center. What happens to the center? Let's say both have the same value. This is radially outward, this radial outward, they cancel each other. Okay, so the electric field in the middle is going to be the center. How about if you take over here? Okay, it's going to be radially outward. Okay, and so the field is this one this way, the field is this way, but this is closer, so it's going to be bigger. Okay, so the electric field will be this way over here. But if you come over here, you see this one is bigger, so you've got a big electric field over here, and this one will be smaller because farther. Okay, the direction will be this way. If you do it over here, you see this will be radially outward, this will be radial but smaller, so it will be something like this. So if you do all the points, that's what we're going to do. You see this line is the separator line over here, so it will be something like this, and it never crosses this line, and the same thing on this side, on this line over here. And the electric field goes away from positive charge and goes toward this, and both of them it's away, and then this is the zero line over here. The electric field is zero everywhere over here, but they will go like this. Okay, so this is the electric field due to two positive charges. For a negative charge, it will be the same thing, except that the arrows will be directed towards the negative charges. So two negative charges. I think that's D, that's E. Two negative charges. So you have negative over here, negative over here. If we take at the center, you see this will be towards this one, this will be towards this one. So the center, they're both equal, they'll cancel each other. So because that the electric field, the x, if you take over here, this will go this way, this will go this way, so the x will cancel each other. So it'll be the same like the plus one will go like this. So we'll go like this, the same thing from here. We'll go like this, okay? But in this case, the electric field point is toward this charges because they're negative charges. Okay, so it'll be like this. Okay, I think over here I said the electric field 0 over here. What I meant was the x component is 0, not the y component. If you take S for example, it will go this way over here, this one will go over here. The x will cancel, so there will be a vertical component. The electric field over here is only 0 over here. All right. Now let's ask one question. Can electric field lines cross each other? Electric field lines cross each other. Let's try to answer this question. Okay, is it possible that you have electric line like this? Okay, so let's look at the intersection point. There should be only one electric field at this point, right? But if these lines cross each other, we're saying if you follow this line, this will be the direction of the electric field. If you follow this line, this will be the direction of the electric field. So that means if electrics cross each other, we're saying that the electric field given point can have two possible directions, which is not possible. So the conclusion is electric field lines do not cross each other because that would imply two different directions for the same electric field. So the conclusion is electric field lines do not cross each other because that would imply two different directions for the same electric field. Different directions for the same electric field. Electric